Hello, and welcome to episode 1 of a brand new podcast called The Math Club. I'm one of your hosts, Noah King. I have been an elementary school teacher for over 20 years, and I absolutely love math, but I'm by no means a professional in terms of mathematics.
And I am your other host. My name is Peter Littig. I am a former math professor, current software engineer, and I also love math.
And we are going to start off with our very first episode talking about absolutely nothing.
That's right. We have lots to say about nothing. And by nothing, we mean the number 0.
That's right. So let's begin, Pete, with a definition in case we have any ancient Romans or ancient Greeks listening who might not have a concept of 0. What is 0?
Well, there's a lot of ways that we could think about it, but probably the way that's super familiar to everybody is 0 is the number we use to mean an absence of things. If we were counting, we would say we don't have any of the thing that we're counting. We have 0 of them.
Right. And is it a number just like any other number?
Yeah, it is. There's some subtleties, of course, but I think it's a very natural number to put in there with the rest of them. Some people consider it to be the first natural number. I am one of those people. And although 0 has a long and interesting history, it has been used in many important ways over time. It really is quite at home with all of the rest of the numbers that we think of when it comes to doing arithmetic.
Okay. Now, here's a question I've been wondering. In preparation for this episode, I did a little reading about 0, and one thing that really stood out to me was that it's really, really an important number, that there's a lot that we couldn't do if we didn't have a concept of 0 to use in our mathematics. So that's my second question for you after what is 0, is why is it so important?
Yeah. Well, I think two things that come to mind immediately. Imagine all of the numbers that you have written down before. They all make use of a positional system of notation, and 0 plays an incredibly important role there. It allows us to indicate a certain position. For example, the ones place, the tens place, the hundreds place, and so forth.
Sure. So we're talking about place value.
Talking about place value.
Something that as an elementary school teacher, I have quite a bit of experience working with kids on.
Yeah. So anytime you write down a number like 1012, you would write that, of course, 1012. Without the number 0 as a placeholder, we wouldn't be able to write that number, at least in that form.
I know what you mean. Like something that's coming to mind is when I'm working with kids on place value and on number sense, there is a common mistake that kids will make if they don't have a strong sense of place value. And that's if I ask them to write down, for example, the number 104. Kids who have a strong grasp of place value will write 104, but kids who don't will hear 104. They'll hear the 1 and the 4, and they'll write it as 14. They'll just write 1 4, and they'll skip that 0, which obviously makes a big difference in what the number that they've written down represents.
Yeah, certainly does. In that case, the number 104, the 0 is playing an important role there. It is telling us that there are no tens in the number. So we have 100, 0 tens, and 4 ones. So it is also, even in this case, indicating an absence of something, right? So the second of the two things that come to mind immediately for me, the first being place value, the second is arithmetic. So arithmetic, which we think of as the addition, subtraction, multiplication, division of numbers. In other words, the number system that we use in day-to-day math depends on the existence of 0 in really important ways.
Like, give an example.
Sure. So, for example, aside from addition, perhaps the most basic operation that kids learn and we use every day is subtraction. Now, if you had a subtraction problem such as 7 minus 4, that would be fine to answer without any reference to 0. 7 minus 4 is 3.
Wait, I know this one. Oh,
okay.
For the record, I was going to say 3.
Yeah, I mostly believe you. So now consider a subtraction problem like 7 minus 10. we all consider that to be a perfectly routine type of arithmetic problem, but the answer depends not only on the existence of 0, but also their negative numbers. So the answer to 7 minus 10 is -3, and we define negative numbers in terms of a relationship between a number and 0. So in this case,
does that mean without 0, we don't even have negative numbers?
We don't have negative numbers without 0. That's right. And there's a little bit of geometry one can attach to this right from the get-go. If I'm picturing a number line, and now I'm just thinking of whole numbers, I like to think of 0 as home base. And picturing the number line in my mind, if I want to leave home, I can go off to the right and enter the world of positive numbers. I take one step and I'm at 1. And if I want to go to the left, which of course, why not? I could take a step to the left and now where am I? Well, I'm at -1, which is to say 1 unit, but in the opposite direction from the positive direction. So if I were to add the 1 and the -1 together, that opposite relationship brings me back to 0.
It's amazing to me to think about the idea that without 0, we don't have any negative numbers at all, because there's so many mathematical tasks that absolutely require negative numbers to be involved. And if you don't have them, you simply can't do them. You know, when I learned that there were ancient civilizations that had no concept of 0, it didn't occur to me that that also meant they didn't have any negative numbers either, and they couldn't do any of that math.
Yeah, and they may have had ways of thinking about negative quantities. For example, if you have borrowed 3 stones or 3 pieces of chicken from somebody, I, by the way, don't often borrow chicken from people, but if you were to borrow 3 pieces of chicken, there's an abstract relationship there between that real world scenario and the number -3. However, to bring that home and put it in the context of arithmetic, I think it's almost certainly true that negative numbers were not operated on in that same way in ancient times.
I can also picture then that the coordinate plane would only have one quadrant. If you don't have 0, it would only have the upper right quadrant.
Yeah, the coordinate line, it would be a ray. It wouldn't be a line. It would just be a ray. So 0, in its most basic form, it is the number that counts an absence of items. It would suggest if I had a box, that the box would be empty. There would be nothing in it. To draw a contrast with, say, having 3 marbles in the box.
And I'm sure that even civilizations that hadn't come up with the number of 0 would certainly grasp a concept of nothing in the box.
Nothingness, yes,
right.
Exactly.
They just maybe didn't have a counting number for it.
Exactly. People like to attach a certain kind of mystical quality or even almost spiritual quality to the number 0. There's an old Taoist idea that goes like this. What makes a vase useful is the emptiness inside, because that, of course, is what the point of a vase is, that it can hold and carry things for us. And in fact, you might say that it is that space that is the creation of possibility. And there's a very neat construction in mathematics that took place at the beginning of the 20th century due to John von Neumann that makes a really dazzling use of this idea of a container that holds nothing. And
what did he say?
So von Neumann, along with many other mathematicians of his day, I'm thinking of Bertrand Russell, for example, Alfred Whitehead, they were interested in laying a foundations for mathematics, and they wanted to rest mathematics on set theory. Von Neumann conceptualized the empty set as actually being the number 0. So now he has a definition of 0. What is it? It is the empty set.
Okay.
And now we want to create the number 1. Oh, I know what to do. Let's grab another empty set and put the first empty set inside it. Now I've got a set that has one thing inside it. And that's what he takes as his definition for the number 1. Continuing, he says, well, I'm going to get one more of these empty sets, and inside I will put 0 and 1. The first 2 objects that I created, I will put them inside my new empty set. It is now no longer empty. It contains 2 things. It contains, and that's the number 2.
So circling that back to your example about the box with no marbles in it, would this be like taking an empty box and that's 0. And then taking another box that has 1 marble in it and putting it into the first box so that you could now say that first box is no longer empty. Now it has 1 thing in it, and that's 1.
You're close, and there would be a way to make sense of that. Von Neumann actually went even simpler, and instead of bringing in different types of object, namely boxes and marbles, he simply said, all we're ever going to work with are boxes.
I see what you mean. So we're taking 1 empty box and we're putting another empty box in it. So now it has 1 thing in it.
Yes.
And if we put another empty box nested inside that second empty box, the outermost containing box now has 2 things in it.
You're right about that. However, that also is slightly different from von Neumann's construction.
What am I missing?
Right. So imagine now I've got a big box and I'm going to put 2 things into that big box. Okay. Are you ready? Yeah. I'm going to put 1 small box and then I am going to put a medium box next to it. And what that medium box has in it is another small box. So now there are a total of 4 boxes involved, but the outermost box only contains 2 things. Yes, one of them also has nested in it another thing. But what this construction allowed von Neumann to do is to construct the entire universe of counting numbers, starting with 0, up to 1, up to 2, up to 3, without limit, using nothing other than empty sets, which he would nest inside one another, and taking unions thereof. In other words, combining them by saying, now I'm going to take all of these littler boxes and now put them in a slightly larger box.
Right.
And so in this very real sense, we see it is the emptiness within that has created the possibility for everything that we take to be the basis of our counting system.
So the next time I find myself saying, oh, I feel so empty inside, I can feel a sense of kinship with John von Neumann.
It's true. It's true. But no, we don't want you to feel empty inside.
Right. Well, this is interesting what you're saying, and it reminds me of something else that I saw in an article that was about 0. And the quote was, we don't often or perhaps ever encounter 0 in nature. And what the author was getting at was the other counting numbers greater than 0 represent things that we actually can see and experience. Like you can see 1 car parked on the street, or you can hear 2 birds chirping in the tree, but that it's very rare to encounter 0 in nature. And I wasn't sure if I agreed with that when I read it. I wasn't sure if that resonated with me, because I think you can also see no cars parked on the street.
Yeah, right. And throughout human history, that would have been the norm. So not seeing any cars.
For most of the 10,000 years,
there were no cars.
There were no cars parked on the street.
Well, I think that's a super cool idea to think about. Like, what does it mean to say that something exists in nature? There's a conceptual leap that humans have to make to say that the 1 car that I see on the street is a representation of this abstract idea of oneness. 1. What is unity? And that's what we mean by the number 1. It's this abstraction that we can apply to any scenario in which we have 1 thing. Same with 2, right? And similarly, to say that 0 is a number in the sense that we have been talking about, hey, this box is empty. Where are my marbles? I'm losing my marbles, Noah. You know, there's a conceptual leap there too, but the history of mathematical development shows us that that was a harder leap to make. It seems very plain and obvious to us now, right?
Right.
We know that that wasn't always the case.
Right. I mean, I can see what the author was getting at. You can't physically see 0 things.
Right.
Or you can't physically hear 0 things. And I think that's what they meant by it doesn't exist in nature.
We can push this to something more physically tangible. Do you know what the coolest temperature is? And I'm talking
absolute 0.
I'm talking really downright cold. It's so cool. 0 Kelvin. So the system that is used by scientists to describe absolute temperature has its origin marked at 0 degrees Kelvin. But certainly ideas like 0 degrees Fahrenheit or Celsius are super common. There is a difference, however, between 0 degrees Fahrenheit or Celsius and 0 degrees Kelvin.
I think I know where you might be going with this. 0 degrees Kelvin is an actual zero. It's a mathematical zero in that there is no movement or
heat energy
at all. Whereas 0 degrees Fahrenheit was kind of an arbitrarily chosen spot on an arbitrary scale.
Yeah, yeah. And I've had some of my best snowball fights right at 0 degrees Fahrenheit. So
I bet you haven't had any snowball fights at 0 degrees Kelvin.
I've had 0. So I think it's fascinating to think what is the physical reality of the number 0.
Right. And I think it's interesting, just going back a minute to that idea that 0 degrees Fahrenheit doesn't really represent zero of anything, or a lack of anything, or none of anything. Fahrenheit could have just as easily chosen a different temperature to label 0 degrees.
Yeah.
And it wouldn't have made a difference. It doesn't really mean none of something other than 0 positive degrees, right?
Right. How many positive degrees do you have?
I remember a student, I live in the Bay Area, and it had been pretty cold in the winter, but it got very warm. And one day it was 35 degrees in the morning, but by the afternoon it had gotten to 70 degrees. Mm-hmm. And a kid said to me, "It is twice as hot right now as it was this morning." And I had to kind of explain, it's not really twice as hot.
Yeah.
You know, the temperature is twice as far from an arbitrary starting point as it was this morning. Yes. But that doesn't mean we have twice as much dynamic motion going on in the universe.
Yeah, and that is a very interesting point, thinking about the way that arithmetic interacts with physical models and the kind of uses we want to put to mathematics. And speaking of arithmetic, within von Neumann's constructions of the natural numbers, there's not much of an inkling that arithmetic will show up. It's really just moving around a bunch of boxes, right? And then you say, oh, look, there's 3 boxes here and so forth.
Right.
Well, what there is within that system is the notion of a successor. If I have a box with various things nested inside of it, and that represents, let's say, the number 7, there is a way to add 1. I take 7 and I get a bigger box, and I put inside that bigger box the number 7 along with the number 6 and the number 5 and so forth, all the way down to 0. And now I've created the number 8. And so inherent in his system is the notion of +1. And
I'm not following that. How, if you take 7 and then add 6 and add 5, how do you get 8?
What I mean is, if you take a box that's big enough, an empty set, and inside that empty set, you put the number 7, and you also put the number 6, and you also put the number 5.
I see. We're
all the way down.
The von Neumann construction that you were defining earlier.
Yes. That set now contains 8 things, and therefore is the number 8. So that process allows me to define +1. What does it mean to add 1 to something? I just explained how 1 could do that. So how do you add 2 to something? Oh, you add 1 twice. How do you add 100 to something? You add 1 100 times.
Right.
And that now gives us a well-defined way to add any 2 numbers together. So starting from that, we can construct the entire world of arithmetic, certainly the arithmetic of whole numbers. Adding 0 in this process amounts to taking the union of one of these sets with the empty set. When you take the union of something with the empty set, you get that something back again. The empty set doesn't add anything new if you take unions.
That makes sense. But I do want to clarify, because it does sound slightly contrary to something you said earlier, but I don't think it really is. So I'd like you to explain the distinction.
Sure.
Earlier we said if you take 1 and 0 and put them together in a set, now you have 2. And if you take 2 and 1 and 0 and put them together in a set, now you have 3.
Yep.
But we're also saying, so in some way we're saying when you add 0 to something, 0 does affect the quantity of things. But that's not really what you're saying, though, is it?
No, because There's a little bit of set theory going on here. But
Because there's a difference between talking about how many elements are in the set and talking about what size the elements are, right?
Yeah.
That's the distinction.
Well, I think to be very precise, the von Neumann construction can be expressed entirely using the language of set theory. Let me just say for a moment what that is. N plus 1 equals N union the set containing N. And if you unravel that definition, it amounts exactly to this idea of nesting boxes and adding more boxes. If N happens to be 0, it amounts to saying take the union with the empty set. Now, that doesn't mean put a set inside another set. It means take everything in your base set and everything in the empty set. Oh, there's nothing there. We'll combine all of that and put it together. Well, I'm not adding anything new because there's nothing inside the empty set.
So this is the property of adding by 0.
Yes. And so von Neumann's construction, not only does it give us a way to do all of ordinary addition of positive whole numbers, it also tells us that 0 is special. When you add 0 to some other number, it has no effect.
Right. Now, there's also a multiplication property of 0.
There is. And I won't go into the details here. There is a way to make sense of multiplication using the von Neumann construction. But multiplication, which is sort of secondary to addition, it's the new guy in town.
Oh, man, there goes the neighbor.
Actually, the neighborhood just gets more interesting. So now you've got two operations, and they want to interact. They want to play together and interact with each other. And as soon as that happens, you have to answer the question of, well, what is 0 going to do?
Right.
And of course, multiplying something by 2 doubles the quantity. What does 0 do? You can show very rigorously, as von Neumann surely would have, that multiplication by 0 gives you 0. It basically levels the field. It sort of annihilates everything. If the neighborhood has gone anywhere, it's not because multiplication showed up. It's because
zero's fault.
It's 0's fault. And in there lies the problem, or not the problem, but the peculiarity. Because 0 does that when it's multiplying, we can't divide by 0. And we have to live with that.
Right. And this is something I definitely have experience with as an elementary school teacher, is trying to teach students why we can't divide by 0. And I actually have a couple of different sort of thought processes that I try to explain to kids to help them get it. And one of them is when we are dividing, like let's say we have 20 marbles. We'll go back to marbles again. And if we divide that by 5, what it really essentially means is that we are dividing those 20 marbles into 5 equal groups, right?
Right.
If we divide 20 by 10, we're dividing them up into 10 equal groups. Well, in order for division by 0 to work, we would have to be able to make sense of take these 20 marbles and divide them up into 0 equal groups.
Right. Right. Yeah.
And that doesn't make any sense. And I think that's why we say it's undefined. There's no definition for how to take an actual physical number of things and divide them up into 0 group.
Right. Right. And so what you're getting at is that all of the intuition we have about what division does, as soon as you try to do that with 0, something breaks. You can show that 0 cannot have a multiplicative inverse. In other words, you cannot divide by 0.
And does that, when you say it cannot have a multiplicative inverse, I think what that sounds to me like is the second thought process that I sometimes use with students, where I remind them that multiplication and division are inverses of each other. They're inverse operations of each other. And so if you were going to say 10 divided by 0 equals what? If you were going to flip that around into a multiplication sentence, that would be what times 0 equals 10.
Right. Right.
And there is no answer to that. There's no number that you can say, take this number, multiply it by 0, and you'll get 10.
And that's because 0 times anything, whatever you propose to put there, automatically equals 0. So now you would be forced into a situation where your equation reads 0 equals 10.
So Pete, then what is 0 divided by 0?
That's an interesting question. What do you think people want to say
Well-
that's equal to.
Well, I think people want to say that's equal to 1.
They do.
And when I take that multiplicative inverse theory, it actually holds up, because I can say 0 divided by 0 equals 1. That means 1 times 0 equals 0. And that works. I can also take 0 things and divide them up into 0 groups. But I don't know that I would say that each of those groups now has one thing in it.
And it seems, by your description, that maybe we have found a sneaky way around, somehow at least saying 0 over 0 equals 1. But if we unravel the definition of division by a number is the same thing. In fact, it is by definition multiplying by the inverse.
So dividing by 0 is like multiplying by 1 over 0, and 1 over 0 doesn't mean anything.
That's the real crux of the matter. It's
interesting.
Even though it looks like you may have found a sneaky way to say 0 over 0 should equal something, it's the fact that 1 over 0 doesn't equal anything that kind of throws the entire operation off the rails. So, unless, of course, you're happy to say that 0 and 1 are actually two names for the same element, and that means
I'm happy to say that.
Okay. Well, for the record, if you were, you would now have a set that has exactly one element in it, namely the number 0, and it's happy to do arithmetic with itself, but it doesn't get to play with anybody else.
No one else will play with 0.
All
right.
That reminds me, by the way, I have a favorite joke.
Go ahead.
What did 0 say to 8?
What?
Nice belt.
That's funny. But it also made me think of one more thing that I would like to ask you about.
Yeah.
Turn that 8 90 degrees clockwise, and now it's infinity.
It's true.
What kind of properties or attributes does 0 share with its somewhat of its counterpart of infinity?
Yeah, it's a bit of a shadowy counterpart, but if you were to say that 1 over 0 should equal something, you might want to say it should be infinity. But you kind of have to leave the realm of arithmetic to do that, and that's fine. One place that division by 0 in this sense shows up is in the geometry of the circle. And so that may seem like, wait a second, how did we get to the circle? But there is a very clever geometric map called stereographic projection that allows us to relate the number line and the unit circle. There's a very nice way to wrap the line around the circle, bringing the ends of the line, which extend out to infinity in both directions, closer and closer to the very top of the circle, the point that I would want to call the North Pole. But they never quite get there because they don't have finite endpoints. So you have a way to associate every point on the line with a point on the unit circle, except the North Pole. So if we put that point in there, if we add an extra point, put it up there, and call it the point at infinity, then there are some interesting things that we can do. In this context, we can ask, what does it mean to divide 1 over 0? And the right answer is to say infinity. The point that corresponds to 0 has as its inverse point the North Pole, this point at infinity.
Interesting.
You get nice geometric properties out of this. You just don't get arithmetic.
Right. Pete, this has been a fascinating conversation about absolutely nothing.
I thought we were going to get together and talk about something, and all we did was talk about nothing.
And I think this was a very interesting first episode for the Math Club podcast. If you enjoyed this conversation, please come back and look for future episodes.
Yeah, I'm looking forward to it. I think this was a ton of fun. And one last thing, I got to say, did you hear about the mathematician who was afraid of negative numbers?
No.
He'd stop at nothing to avoid them.
Oh, good Lord. All right.
Thanks for
listening, everybody.
Up from Seattle. Bye.